Swayam Prabha. Digital India. Educated India.
Okay, so let's start the lecture today, and want to continue from where we left off, in fact with a small rewind and recap. So, the problem that we were interested in is how does the flow go to steady state from an initial condition, okay, and that is the problem we are trying to analyze. We are interested in the developing in time. How does the flow develop from a quiescent state where there is no movement to the steady state parabolic velocity profile. So, rather than solve that direct problem, what we did is we said we will look at what is the deviation from the steady state, and then we can, if you know how far it is from the steady state, we can find out the problem by adding the steady state to it, okay. So, so that is what we did. We wrote the problem as a steady state problem multiplied by, how far, so Vz is the actual velocity, and we are looking at the deviation from the steady state, which is the parabolic velocity profile. So, this is the parabolic velocity profile, this is the actual velocity, and this is the deviation. Now, the advantage is that when I look at it this way, the equation which governs W turns out to be a parabolic initial condition problem, okay. There is a minus sign here. Oh no, there is not a minus sign here, she is written as r squared minus 1, it is fine. So, so this now becomes, the initial condition is non-zero, the boundary conditions are homogeneous. So, this is basically a parabolic initial condition problem. So, I want you to understand that this transformation, rather than solve, if we solve for Vz, it was a non-homogeneous equation problem, because the non-homogeneity, the pressure gradient was in the equation. But Vz also has the pressure in the equation. So, when I subtract it, that goes off, and this is what I get, okay. So, this equation, this is governed by a non-homogeneous equation, and this W is governed by a parabolic initial condition, which you know how to solve, and this was an ODE, which gives you the laminar profile, and of course, all these equations are all linear, okay, which makes it possible for me to solve it analytically. Otherwise, I have to write some computer code or something. So, that is the idea. So, this whole business of looking at the deviation from the steady state helps me convert a non-homogeneous equation problem for Vz into a parabolic initial condition problem for W, and this we solve by the separation of variables, okay, and that is what I wrote last time, R of R times theta of t. So, we seek W, which is a function of R and t, as a product of two functions, one only of R, one only of time, and if this has to be a solution, this has to satisfy the differential equation, okay. So, I have substituted this in the differential equation here, and I get R of R multiplied by theta dash of t. This theta dash is derivative with respect to time, okay, because this is partial with respect to time, I get that, then I get 1 by R d by dr of R dr by dr times theta. Again W are substituted here, and theta is a function of time, so I can take it out. capital R is a function only of R, so I don't write partial derivative, I write total derivative. Okay. So here I wrote partial derivative because W is a function of R and T, but capital R is a function only of R. Theta is a function only of T. So now you divide this thing throughout by theta R. Divide by theta multiplied by R. What do you get? Theta dash divided by theta equals 1 by R times R of R dr by dr. This is what we saw last time. Okay. So the theta got cancelled, R is there, R got cancelled, theta is here. Now what we argue is that this is a function only of time, this is a function only of R, and that can happen only if this is equal to some constant, and we introduce this negative sign because like we did in the math course, because we want functions to asymptotically approach steady state. If, for example, a simple way to think about it is, if this is plus lambda squared, okay, then the velocity is going to blow off to infinity. As time goes to infinity, you will find, so the solution to this is theta dash equal to minus lambda square theta, or theta of t equals theta naught times e power minus lambda square t. Lambda square of course is positive. So I mean, one way to physically understand this is negative because you want the solution to go to 0, you want the deviation from the steady state to go to 0. As time goes to infinity, okay, I want W to go to 0 because only then my solution will go to steady state. Okay, my solution Vz has to eventually go to steady state, so I want W to go to 0, and that will go to 0 as time goes to infinity only if this is minus. If this is plus, it will go off to infinity, you won't go to steady state. Okay, that is a physical way to look at it. Mathematically, of course, you argue that you get an eigenvalue only if there's a minus sign here. Okay, we have done this before in the math course, how to decide the sign plus lambda squared or minus lambda squared. Okay, so that's what it is. Now, so this is the solution for theta. The solution for R is going to be given by 1 by R d by dr of R dr by dr plus lambda squared R equal to 0. Okay. Now, what I want to do is recognize that W has to be 0 at R equal to 1. Okay, and W is defined like this. So if W is 0 at R equal to 1, that means capital R at R equal to 1 must be 0. Okay, capital R at R equal to 1 must be 0, only then W will be 0 at R equal to 1. So the boundary condition for this is R of 1 equals 0 and R of 0 is bounded. Okay, so that's what it is. Now, what you got to do is, we don't know what this constant lambda squared is, and the way you find this is you find the solution to this problem. The solution to this problem is given by C1 J0 of lambda r plus C2 Y0 of lambda r. And this is a very classical problem. I mean, we have done this again in the math course, where we looked at all these eigenvalues as coming from a Sturm Liouville problem. Okay, and we know that in the cylindrical coordinates, the solution to this equation is of this form. Okay, I mean, one way to look at it is, now some of you were not in the math course. One way to look at it is, in Cartesian coordinates, you get sine and cosine, okay, which have a power series expansion. This J0 Y0 also has a power series. So, I mean you can do this thing by using this Frobenius method and get a power series solution. That particular power series is identified like this. This is a Bessel's function, also a Bessel's function of a different kind. Thing is, this is unbounded. Unbounded means it goes to infinity at r equal to 0, okay, unbounded at r equal to 0. And since my solution has to be bounded, I put C2 equal to 0. Therefore, C2 must be 0, okay. And so R of R is equal to C1 J0 of lambda R. And how do you find the constant lambda? You have to satisfy this boundary condition, R of 1 must be 0, okay. So, R of 1 equals 0 implies C1 cannot be 0, J0 of lambda must be 0, okay. Now, of course, today you have all these powerful tools, computational tools, MATLAB, Mathematica and all of that. You can go to one of these tools and you can just say plot this Bessel's function J0 of order 0, okay, and it will plot. If you do that, what you will get is J0, if you want to plot versus J0 of x or J0 of lambda, if you plot versus lambda, you will get something like this. Point is, all these points are the points where the Bessel's function is 0, okay. If you had sine n pi sine lambda x, okay, you know that, or sine lambda, because you are going to impose the boundary condition at x equal to 1, sine lambda equal to 0 means lambda is n pi. So, you have an infinity of roots. Similarly, here Bessel's function has an infinity of roots, okay. So, but these have to be found numerically, and again all these computational tools will help you find all these zeros, okay. So, basically this corresponds to lambda 1, this corresponds to lambda 2. So, you have an infinity of roots. So, we have J0 of lambda n equal to 0 for n equal to 1, 2, 3, etc. You understand? So, because I want the Bessel's function to be 0, it is 0 at a few points, okay, and if you want to plot it and look at it, you can get it, but there are ways to do it computationally, okay. For example, this is a function, so you can do Newton-Raphson method, and this is algebraic equation. So, you can do Newton-Raphson method and you can get the roots. So, that is one way to do it, okay. So, anyway, so these roots can be found and these roots are your lambdas, okay. So, now what am I left with? So, now I found the lambdas, okay, and so I have W of r comma t is what we said, theta of t multiplied by r of r, and theta of t is nothing but C naught e power minus lambda square t minus lambda square t times C1 J0 of lambda n r, okay. Now, the point is, I will have an infinity of these solutions, okay. So, basically and each of these solutions is going to be associated with an arbitrary constant. So, this constant C naught multiplied by C1 e power minus lambda n square t J0 of lambda n r is going to vary with n. I have a particular n, I have a particular 0, I will have some, this constant is arbitrary right now, I do not know what it is. It does not have to be the same. I have to recognize that this constant can vary with n and be sufficiently general, okay. So, I am saying this is going to be a function of n, okay. So, the point is W of r comma t can be written as a n e power minus lambda n square t times r of lambda n r. Okay, but this satisfies what? The boundary conditions at r equal to 1 and 0, okay, and I will have many of these, and because this equation is linear, a linear combination of all of this is going to satisfy my equation, and I write this as summation n equals 1 to infinity. Okay, I write this as n equals 1 to infinity, and what this means is this satisfies the boundary conditions. This particular expression that I found satisfies the boundary conditions in the r direction. The only thing it does not satisfy is the initial condition, which you had written here, minus 1 minus r squared. Okay, so the initial condition is yet to be, oh wait a second, this will be J0. Man, people are all sleeping. This is J0. Yeah, that's J0. Yeah. To be satisfied. See, we've ensured that the differential equation is satisfied because I substituted it in the differential equation. We have ensured that the boundary condition r equal to 1 is satisfied. We have ensured boundedness. Initial condition I have not talked about so far. So, I am going to look at the initial condition, and that is 1 by 4 of 1 minus r squared with a minus sign at t equal to 0. If I put t equal to 0, I get a n times J0 lambda n r, n equal to 1 to infinity. So, this is like my Fourier series. Fourier series, you normally know to think of it in terms of sin x and cos x, that is in the rectangular Cartesian coordinate. In the cylindrical coordinates, this is a Fourier series, Fourier Bessel series. Okay, so this is my Fourier series now, and I need to find these constants a n, and you use the orthogonality property. Only thing is, this orthogonality property now is with respect to the weight function r. Okay, so what you do is, how do you find a n? A n is, you take the you multiply both sides with J0 lambda n r, integrate, and some orthogonality relationship is there. So, what you get is minus 1 by 4 times 1 minus r squared times J0 of lambda n r multiplied by r, okay, dr, integrating from 0 to 1. This r is important because the orthogonality is only with respect to that weighting function as per the Sturm-Liouville theorem, okay, and this is divided by integral r J0 squared lambda n r dr from 0 to 1, okay. So, I mean mathematically you talk in terms of taking the inner product. The orthogonality of these Bessel's functions is with respect to a weighting function r, okay. If you do not want to get confused by all of that, you will just say I multiply, the orthogonality is only when I multiply it by r times J0, okay. And this same thing what you do when you do Fourier sine series, cosine series, you will, how do you find this coefficient a n, b n? You will just take the multiply by sin n pi x, but there is no r extra r added, okay. Anyway, so this is how you find the a n. Once you know what the a n is, you can substitute back inside here and find w. Once you know what is w, you know the solution Vz. It is w plus Vz ss, steady state, okay. So, I hope this is clear. I found one solution, and there are infinite roots, okay. So, everything is going to be a solution, lambda 1 is going to be a lambda 1 r, lambda 2 r, everything is going to be a solution, okay. E power minus lambda 1 square t, lambda 1 r is going to be a solution. E power, I just put lambda, okay. lambda 2 squared J0 lambda 2 will be a solution. So, all of this I am adding together, and I am saying my solution is composed of a linear combination. These coefficients depend upon n, and I find the n by doing this inner product. Okay. So, now I know W, and I can find Vz. Vz of r comma t is Vz SS plus W of r comma t. Vz SS depends only on r. Okay. We want to find out Vz. So, the question is, I said I want to find out how much time do I have to wait for the system to go to steady state. That is one of the questions which we are interested in. We have to wait for, and what is going to decide this? If I were to arrange the lambdas, if we arrange the lambda ends so that lambda 1 is less than lambda 2 is less than lambda 3, etc., okay. If the lambda is very large, what is going to happen? The contribution W, remember, is if the lambda n is very large, it is quickly going to go to 0 because e power minus a large number times t. So, the one which is going to give you an idea of how much time it takes to go to the steady state is going to be the lowest eigenvalue. Okay. So, basically what I am trying to tell you is lambda 1 is a measure of the time taken to reach steady state. So, so this tells you this is the one which is going to take a lot of time to go to 0. Eventually, everything is going to go to 0. The one with the largest eigenvalue, largest lambda n will go to 0 immediately because this is multiplied by a large value, but the one which is lowest is the one which is going to take a lot of time to go to steady state. So, I am saying if you want to get an idea of the time constant of your system, how much time do you have to wait? To get an idea of that, you just need to look at lambda n, okay, and the reciprocal of lambda n squared. So, the reciprocal of lambda n squared, because this has units of time, lambda, this has to be dimensionless, lambda n squared has units of 1 by time, okay. The reciprocal of lambda n squared, that is an estimate of the time taken, I must say lambda 1 squared, okay, time taken to reach steady state. So, if lambda 1 is very, very low, it will take a lot of time. If lambda 1 is very, very high, it will go to steady state very quickly, okay. So, if lambda 1 is low, so if lambda 1 is low, we will take a long time to reach steady state because this time is proportional to 1 by lambda 1 squared. If lambda 1 is high, we will take a short time to reach steady state. Okay, I have arranged my lambdas in an ascending order. So, lambda 1 is the one which decides, the time taken. All the others are going to go even faster. So, normally you will say, look, if my steady state temperature is 100, to reach 100, I may have to wait for an infinite time. But you may say, look, I am okay with 1% accuracy. If 99, once it reaches 99 degrees, velocity is 99 centimeters per second, is 100 centimeters per second. I am saying very close to steady state is good enough for me. So, you can decide what is good enough for you. Do you have to wait till it goes exactly to steady state, or within 1%, within 0.1%? Okay. So, that tells you the things, because to make W 0, you have to wait for infinite time. So, you might say, look, the deviation from the steady state I want to be 1%, 0.1%. So, you specify that and you can get an idea of what the time is. Okay. So, this is basically a transient problem which we have solved, and because it is linear, we have been able to get some insight about the time taken for it to reach the steady state. Okay. So, this is what we have done is a fluid mechanical problem where the pressure drop was imposed and we looked at the time taken for the fluid to go from rest to some final steady state value. Now, we want to look at some analogous situations in heat transfer and mass transfer. Okay. And so, let us see what I wanted to spend some time, because this is a transport phenomena course, we should do that. So, what is an analogous problem in, let us say, heat transfer? Okay. Now, so we are talking about heat transfer problem. Let us say again we stick to a cylinder 0 to R naught. Okay, this is the radius, and let us say there is an ambient temperature T ambient. Okay. So, if you were to write the energy balance equation for this problem, okay, and we have a solid cylinder here, this is solid. The only method of why am I keeping it solid? Because the only mechanism of heat transfer is going to be by conduction. Okay. So, only mechanism for heat transfer is by conduction, and that is the same thing that we had. The only in the earlier problem we had when we did the fluid flow, the only mechanism of momentum transfer was by viscous term. Okay, the viscous term, remember mu 1 by r d by dr, that is like a conduction term. Okay. So, now if you want to write the equations here, and you have to believe me, but you do not have a choice today. This is going to be the equation for the heat transfer, okay, the energy balance equation, because there is no velocity, you only have the time derivative, unsteady state, you have the thermal conductivity term, and this has to be solved subject to some boundary conditions. Okay. The boundary conditions are going to be, what will be the boundary conditions be? Temperature at R equal to 0 is bounded, and let us look at the problem which is temperature at T equal to temperature at T equal to 0 is, let us say, T initial, and the boundary condition R equal to R. Okay. What will that be? R equals R naught, was R naught? Yeah. Boundary condition is minus K n dot del T equals H times T minus T ambient. Okay. I've written it in a general form. I am going to write it specifically now. This is basically n is going to be the direction of the outward normal. This is n, the direction of outward normal, and in this case the outward normal is in the r direction. Okay, so this is basically minus k er dotted gradient of t equals, and so this the left hand side tells me the flux of heat coming from inside, the conductive flux from inside the cylinder to the surface. This is balanced by whatever is being lost from the surface to the ambient in terms of the Newton's law of cooling. Okay, this is the heat transfer coefficient, and the temperature difference tells you how much is the heat that is being lost. Okay, so this is basically what it is, H times T minus T ambient, and you can expand the gradient of T as Er d by dr plus E theta by r d by d theta plus Ez d by dz, and what you get, because Er dotted with Er is 1, Er dotted with E theta, Er dotted with Ez is 0, okay, you get minus k dt by dr equals H times T minus T ambient. Okay, this is the boundary condition which you are going to use. In the limit of H tending to infinity, means suppose the ambient air is not stagnant, you put a fan and you really at a very high speed, the air is moving, so heat transfer is very, very high. What can you do? You can divide this whole equation by H, and H goes to infinity, so the left hand side goes to 0. Okay, divide by H, and we get T equals T ambient. Why am I doing this? Because this is basically by Dirichlet condition. Okay, I am specifying the temperature at the surface as being equal to the ambient temperature. So this is, in the mathematical parlance, we call this the mixed boundary condition or the Robin boundary condition. Here this is a Dirichlet condition. And I wanted to bring out the analogy with the fluid flow problem, where I said the velocity was 0 because of the no slip boundary condition. So in the fluid mechanical problem, when I specified Vz equal to 0 because of no slip, that is a Dirichlet condition. Okay, so to make this analogous to that, I am taking the limit of H going to infinity, because now I also have a Dirichlet problem. Okay, so now, this gives me a Dirichlet condition in at r equal to 1 or r equal to r naught, it does not matter. And my problem is rho Cp dt by dt equals k by r d by dr of r dt by dr. Okay, and boundary condition and temperature at T equal to 0 is T initial, and temperature at R equal to 1 is T ambient. This both the initial condition is non-zero and the boundary condition is also non-zero, but what I can do is I can define a T star as T minus T ambient. T ambient is constant, okay. It's not changing with time or this thing. So, this is just a constant. So, what happens? I can substitute for T here. Okay, I can substitute for T here and write everything in terms of T star. Supposing I do that, what do I get? Okay, all I have done is substituted for T star here, and what is the advantage of this? T star at T equal to 0 equals T initial, T is minus T ambient, and T star at R equal to 1 is 0. Okay. So, basically, I mean, I am able to do all of this only because my equations are linear. And if you remember, I said we use the principle of linearity and superposition when you have two non-homogenities, okay, and then we can we treat one non-homogeneity at a time when you, because the equations are linear. But what have I done by making this transformation? I had two sources of non-homogeneity. By making this definition, defining T star like this, I have only one source of non-homogeneity now in the initial condition. Okay. So, this is a parabolic initial condition problem. Agreed? Because the differential equation is parabolic, this is a parabolic initial condition problem. Only the initial condition is non-zero, boundary condition is homogeneous, this is homogeneous. Differential equation is homogeneous, this is non homogeneous. Okay. So, now you know how to solve it. So, but my question to you is, what do you think is going to happen to T star? What will T star be if you wait for a long time? If we wait for T to go to infinity, what will T star be? What will T star tend to? That is the question. T star, I am going to argue, is going to tend to 0, okay, because the boundary condition is, in the boundary my temperature is constant, temperature T star is 0 at the boundary, and if it is going to be different anywhere inside, if it is more, supposing temperature is more inside, because of conduction heat will get dissipated and it will become uniform. If it is less, heat will come from outside and it will increase. Okay. What does thermal conductivity do? It makes the temperature uniform. Okay. Just like diffusion, if you put some sugar in the middle, you wait for a sufficiently long time, because of diffusion the entire water is going to be sweet. Put some sugar in the in water, you mix it, it becomes sweet very quickly because you are stirring it. But if it is only diffusion, you wait for a long time, the entire sugar will have a uniform concentration, because any changes in the concentration will get smoothened out by diffusion, any changes in temperature will get smoothened out by thermal conduction. Okay. So, my point is T star will go to 0, okay, because the thing is 0. But so this is not really an analogy in the sense, I mean, in the steady state problem I got a velocity profile, okay, which is because of the non-homogeneity in the differential equation. So, how can I, what would be an analogous situation for here, where I am going to get a non-uniform profile? So, I need to have a source of heat, source of energy in the solid, only then I will get some kind of a parabolic profile or a non-uniform profile. So, one way to physically understand that is, supposing you are passing some electrical current, okay, and because of, let us say, Joule's law of heating, okay, there will be some resistance in the solid. So, heat is going to be generated by Joule heating, okay, which you have studied in physics. So, if this source is uniform everywhere, then there is going to be an additional source term here, which I have to include. If I include that source term, that is the equivalent of my dP by dx which I had in my fluid flow problem. In the fluid flow problem, my dP by dx was my non-homogeneity which was driving the flow. So here I am saying we need a heat source to make this profile analogous to the fluid mechanical problem. Okay, that is dP by dx is the momentum source we saw. So Q is the heat source, and if you heat source per unit volume, so then, and this can come by, let us say, joule heating when a current is passed. Okay. So, I mean, of course, you can have an exothermic reaction which can also be generating heat, because our chemical engineers will talk, but the problem is the rate of heat generation depends upon the temperature because of the Arrhenius temperature dependency. So, that becomes non-linear. Okay. So, anyway, so this is the heat source, then the equation gets modified, and this is the plus Q. Okay. So, this becomes your heat source, and that is the same as what you had, minus dP by dx in your earlier problem, source of momentum which is driving the flow. So, here there is some joule heating which is generating heat, and that is getting dissipated to the atmosphere, and you will get a parabolic profile. Okay. So, I mean, these are things which I wanted you to think about as an analog of what we have seen in fluid mechanics to heat transfer. Similarly, what is the analog in mass transfer? Okay. So, let us say you have a cylinder, and this cylinder now is a catalyst pellet. Okay. So, and let it, again, to keep life simple, I am going to assume that the reaction that is happening inside is a zeroth order reaction. Reaction occurring is a zeroth order reaction. Okay. And typically what you would do is, and let us say the external mass transfer coefficient is high. For example, your Sherwood number is very high, you are stirring it, or you are making the gas or liquid flow at a very high rate. So, there is no mass transfer resistance. So, that is the same as my heat transfer being very high, H being infinity. Okay. So, the boundary condition will be minus d dC by dr equals Km times C minus C ambient. Okay. And again I will put, if Km is large, this becomes C equals C ambient. So, I get my Dirichlet boundary condition again. in the limit of large mass transfer coefficient. I am trying to get to something similar to my Dirichlet condition for velocity, the no slip condition. Okay. And what will be the differential equation for this problem? dC by dt equals d by r d by dr of r dC by dr minus k. What is this k? This is a reaction rate constant. I am assuming my reaction rate is 0, I mean my order is 0, and therefore the reaction does not depend upon concentration. Okay. What I have written is for the reactant, this is for the reactant. Only thing is because the reactant is getting consumed, whereas in the earlier cases it was a heat source was there, so I put plus q. Okay. So the point is this equation is again very similar. I needed to have a source for the reaction, for the mass transfer, for mass generation or mass consumption, that is here. Boundary condition is similar. Okay. Initial condition could be concentration 0 initially. So this problem is exactly analogous to my this thing. So if you want to try and solve this problem, you can use the same principles that we did for the fluid mechanical problem, for the velocity. Okay. The velocity, how does it change from time t equal to 0 to the steady state? We did something. Same approach can be used to solve this heat transfer problem and the mass transfer problem, because they are very similar. Okay. So you have a non-homogeneity, this is a non-homogeneity, this again is a non-homogeneity, and you have some initial conditions, boundary conditions. Boundary condition I made it same as u equal to 0 by assuming heat transfer coefficient is large, mass transfer coefficient is large. Okay. So boundary condition became same, and you just, and I told you can do some tricks like T minus T ambient to make it homogeneous. So you should be able to basically use the same methods before. Okay. So this is the analogy which you have to understand, so that you can feel equipped to solve problems. So you don't have to think of new methods for every problem. Okay. I wanted to I'm just going to tell you what we're going to do in the next class. We won't do it now, but this is a small difference. So we're going to do the pulsatile flow problem. Where delta P is a periodic function of time. So this is again a time dependent problem. Okay. But now my focus is not going to be on how does it change from the initial state of rest to the final state, because the final state is going to be periodic. If my pressure is going to vary periodically in time, my velocity is going to vary periodically in time. Okay. So here our focus will be on what is the final periodic state. So this is analogous to what is the final steady state. As t goes to infinity, I go to steady state if the delta P is constant. Okay, and you know what the steady state is, that's the laminar profile. But if it is varying periodically in time, my final state is going to vary periodically in time. I want to find that final state. I am not interested in how I go from 0 to this thing. My heart is beating for last 50 years, more than that. Okay. So who cares how it was the first one day, right? I want to know how it is beating now, how is the flow now. So that's the point. We do not focus on the trajectory from t equal to 0 onwards. So, that is a slightly different focus area we have. Earlier focus was on from initial state to final state, what is the time required. So, we talked in terms of eigenvalues. I told you the first eigenvalue gives you an idea of what is the time constant. Now, we say I do not care about the time constant, my thing is at large time, what is my final state? My final state is not going to be a steady state, it is going to be a periodic state. And how do I find that periodic state? We will do that next week.